Hello and welcome to another episode of How to Understand X. Today we're going to be talking about some more methods of integration. Again, integration is one of the most fundamental operations to calculus, so there's obviously going to be a lot more than just what we talked about in that previous video. And even what we did talk about in that previous video, I feel like I didn't talk about too much. So we're going to do some examples of integration by parts, partial fraction decomposition, and improper integrals. I think we're going to start with integration by parts because I feel like that's most likely going to be the most easy to translate from what we talked about in the actual integral video. So let's do that. As we said, u dv, or the integral of u with respect to v, is equal to uv minus the integral of v with respect to u, or the antiderivative of v with respect to u. Now, we proved this using product rule. So, well, it doesn't hurt to just review that proof real quick. It's if u v prime, the product of two functions u and v prime, is equal to u prime v plus u v prime, then if we take the integral of u v prime, or, maybe I should use dx notation. But let me just say u is equal to like f of x, and then v is equal to g of x. These are functions that take x as input, so we can differentiate with respect to x. And then we have the integral of u prime v with respect to x, and u v prime with respect to x. Not times x, just with respect to x. Nope, that's not what I want to do. There we go. Dx. Alright, and now we simply get uv because derivative of an antiderivative, the antiderivative of a derivative is just going to be the original function times the derivative of u with respect to v dx. Well, we actually don't need to change any of this. Let's just say that let's not use f of x and g of x. Let's use u of x and v of x, so it'll be easier to see what we're about to do. And v equals v of x. Now, if we differentiate both of these with respect to x, you'll get du is equal to u prime x dx, since we're going to be differentiating both sides with respect to x, so d du and then d dx, and then we have dv is equal to v prime x dx, and so from here, this is equal to u prime x dx, so this will be v du, and then plus u v dv, right, because this is v prime dx. And now once we subtract both sides by v du, you're just going to go straight back to here. It's not u v dv, it's just going to be u dv. And we're just going to be left with u dv, that integral of u with respect to v, is equal to uv minus the integral of v with respect to u. So yeah, it's relatively self-intuitive. It's just going to be the way to end chain rule. Not chain rule, product rule. We can undo chain rule using u sub, where we just substitute a function for another function and then differentiate with respect to the function instead of respect to x. But integration by parts is how we're going to integrate products of functions. Now, let's do some examples so it's a little bit easier to see. First one that we're going to have to do, I think I might have actually done this example, but it does not hurt to redo it, is ln x of dx. As a general rule, you want u to be easier to differentiate, and then v is going to be easier to integrate. The reason that we do this is because we have u dv is equal to uv minus the integral of v to du. If du is nice and simple, then we don't have to do too difficult of an integration of v. And these are just general rules. You're not going to always have perfect functions where u is easy to differentiate and v is easier to integrate. But for that, there might be some other formulas that we can use to make it a little bit easier to look at. But I think it makes some good sense to have u be easy to differentiate, right? Because if u is easy to differentiate, then our du will be nice and simple. Like imagine if we had, well, let's look at this problem right now. What is ln x dx? It looks like it's just one function. Dx is, again, not a function, it's an operation. But ln x is one function, but anything by itself is also ln x times 1. Because, if you have a is equal to a times 1. And if you're ever in one of these situations where it's most likely going to use integration by parts, then you're going to have to do, you're just going to have to think about 1. That's usually a good place to do it. So ln x times 1 dx. Now, which one is easier to integrate? Well, we only have two functions, so it's a pretty easy choice. ln x is what we are trying to integrate, so we obviously don't know how it's going to integrate. But 1 is easy to integrate, right? It's just going to be 1 over 0 plus 1, because again, 1 is equal to x to the power of 0, times x to the 0 plus 1. So 1 over 1 times x to the 1, so x. And then from here, we have, this is going to be 1 dx, right? This is the integral of 1 with respect to x. So this is going to be the derivative of v, right? This is going to be dv is equal to 1 dx. And then u is going to be equal to ln x. Remember, our original starting function is going to be the integral of u with respect to v. So we have to find our u and we have to find our v, and we have to go from there. So we have to have u and dv. That's going to be the first things that we look for in our situation. And now we have to do du and v, right? Because in our output, we're supposed to have a uv, and we're also supposed to have a v and a du. So how do we get v and du? Well, dv, or the derivative with respect to v, is going to be the integral, v is going to be the integral of the derivative, right? Because antiderivative and derivative are obviously inverse operations. So when we integrate dv, or when we integrate 1 with respect to x, we're just going to be left with x, as we said, 1 over 0 plus 1 plus times x to the 0 plus 1. And then from here, we have du. We're going to have to differentiate u with respect to u, and that's going to be ln x with respect to x. So what's the derivative of ln x? Well, it's going to be 1 over x dx, right? And from here, we just need to plug in everything. We have uv, so u and v, that's going to be x ln x minus v du. So the integral of x times 1 over x dx, right? And we simply cancel out our x's, and we're left with x ln x minus the integral of 1 dx, which again, we said was going to be x. So we're left with just x ln x minus x plus c. And just to make sure we're right, you don't have to do this for every problem, but it does definitely help to make sure. I think at a certain point it might be easy to just kind of do these in your head, but it does not hurt to practice our derivatives. We're just going to do the derivative of x ln x minus x plus c just to make sure. So we're going to have x times, x prime times ln x plus x times ln x prime minus x prime plus c prime. So we did product rule for this, and then we just did the derivative of those two, right, to find the derivative of all of this. And now x prime is going to be 1. It's 1 times x to the 1 minus 1, so x times x to the 1 minus 1 is going to be x to the power of 0, which is 1. So 1 times ln x plus x times 1 over x, as we said, minus 1 plus c. And then from here, we're just going to be left with ln x, c prime, which, forgot to say, derivative of a constant is 0, so plus 0. Again, I feel like I've said this a million times, but if we have y equals a constant value, then any point that you pick, the tangent line will have a slope of 0. I think it's relatively intuitive because every single tangent line will just be a straight horizontal line. And then we have ln x plus 1 minus 1, which is just going to be ln x, which is good, you know. Integral is the antiderivative, so if we differentiate, we should just get our original value. Let's do a couple more integration problems, just so that we know some tactics that we can use. There's something called tabular integration that we will talk about. I'm personally not the biggest fan, though I do understand it relatively well. It's not like it's a trick, or, well, it is a trick, but it's not like it's bad math or anything, you know, like it works. It definitely works, and you can kind of see how it works, but not the biggest fan of it. I just feel like it doesn't make as much sense to me as integration by parts does, at least because I know what the proof of integration by parts looks like. So, yeah, let's do some more integration by parts practice problems. Let me just search that up. Alright, we have the integral of x to the power, x times e to the power of 2x dx. Now, what's going to be easier to integrate here? Well, that's going to be a harder question, but let's just set up our u, v, du, and dv. Those are the 4 things that we need to know before we can do anything, right? Now, this is a matter up to debate. Some people might consider e to the power of 2x easier to integrate because it's just going to be, well, let's look at our derivative rules. We know that x to the power of n, this integral is going to be 1 over n plus 1 times x to the n plus 1. Again, if the derivative of x to the power of n is equal to n times x to the n minus 1, we want this n plus 1 and n plus 1 to cancel out so that we don't get anything in front of the x, right? Because that should be, 1 or some constant, which would be up here. But from here, the opposite of n minus 1 is going to be n plus 1. It's going to be opposite operations. And then division is obviously the inverse operation of multiplication. So that's going to be the derivative, or the antiderivative of x to the power of n. And then e to the power of u is going to be u prime times eu. So if this is ddx, or not ddx, this is going to be ddu of e to the power of u. It's going to be u prime times e to the power of u. This is chain rule, because if u is a function, you have to do g prime x times f prime of g of x. So from here, let's just do the antiderivative of e to the power of u. So let's actually do a quick little u sub. Well, actually I don't think u sub is going to be too necessary for this one. It's just going to be 1 over, you know what, actually, I think it's helpful to do u sub. Let's use 2x as our example. we have the integral of e to the power of 2x dx. So if u is going to be set as our 2x, let's differentiate both sides. So derivative of u is obviously going to be du, so with respect to u. And 2x, the derivative of 2x is going to be 2dx. I think it's probably just good to remember at this point that the derivative of x is always going to be 1. No, like x by itself. That's because if you have like a linear function, like again, if this was 2x, and you drew a point, and then like just try to find a tangent line, the slope of that tangent line is going to be a constant, right? So 2dx, and then from here you can just have 1, well, let's solve for dx, we have 1 over 2 du. So we bring that out front, like we're going to have 1/2 times the integral of e to the 2x, or not 2x, it's going to be u, because we're using u now with respect to u, so that's going to be just 1/2 e to the power of u. So e to the power of 2x. So this is just going to be 1 over u prime times e to the u. And that makes sense, because if we did the derivative of u prime, we're just going to be left with, well, I'm not sure if this always works. We might do some examples where this isn't going to fly, but just as a general rule, we're probably going to have to use u sub. But I think that's a relatively okay rule to have if you have. That actually shouldn't be a rule. I'm not going to put it as a rule. Just like, I think for most Calculus 1 students, that will probably be okay. But once you get into more difficult U's up there, I don't think that's going to work out. So, I mean, obviously now, it's not going to be easier to integrate e to the power of 2x. Even though we did get a relatively okay like thing at the end, e to the power of 2x is going to be a lot easier to integrate. That means that, oh, sorry. Wait, what am I going to do now? Actually, let's see. Since we're only doing one integration, I think I'm actually going to let u equal x, and then du be 1 dx. Again, as we said, we want to remember that the derivative of x is going to be 1. I think this might be slightly easier to integrate. I don't know. Because if we have this u with respect to v, and we're getting uv minus the integral of v with respect to u, if du is just going to be dx, so if you have an x and you just get a du, regardless of what your v is going to be, I feel like it'd be a lot simpler. So, yeah, let's do it. As we already kind of talked about, the integral of e to the power of 2x is going to be 1/2 e to the power of 2x. So if that was u, this is going to be u prime, so 1 over u prime times e to the u, which again is not a rule, it's just an idea that we kind of came up with. And then from here, we get, well, let's just plug in everything into our function, or expression. We have, this is uv, or u dv, so we're going to have uv, so x times 1/2 e to the 2x minus the integral of v with respect to u. So that's going to be 1/2 e to the power of 2x dx. Now let's just bring this out there. So we're left with, let's put this all under, well, let's have just 2 in our denominators, and like, let's have constant in our denominators. We're going to have 1/2 times the integral of e to the power of 2x dx, which again we said was going to be 1/2 e to the power of 2x. We could do the work for this, but we already kind of did. So x e to the 2x. It's not x to the power of e to the power of 2x. It's going to be just x to the x times e to the 2x over 2 minus 1 half times 1 half e, it's going to be e to the power of 2x plus c. So this is just going to be x to the, I don't know why I keep writing x to the e to the 2x. It's not, maybe I'm just used to something else that we might have to do. X times e to the power of 2x over 2 minus 1. Oh, we want to keep our notation constant. E to the power of 2x over 4 plus c. And that's one of our answers, so let's see if we got it right. See if we got it right. Yeah, okay, good. Now let's have, this one's interesting. We have x times e to the negative x dx. Okay. Well, equal x e to the negative x dx. Alright. Let's set up our u, our v, our du, and our dv. So for this one, what is our u going to be? It's going to be easier to differentiate, and our dv has to be easier to, so u has to be easy to differentiate, and dv has to be easy to integrate. Well, as we said, x is probably our best bet for u, because once we differentiate u equals x, we're just going to get du equals dx, or du equals 1 dx. But we don't need to write the 1 at a certain point. Du equals just dx. And so when we do v du, regardless of how complex v might be, since du is only dx, we don't need to alter v too much to get a more normal looking integral. So even though I know that e to the negative x dx isn't super easy to integrate, it's probably going to be a lot more simple to do VDU, because again, let's just do this real quick. We have u equals negative x, so if we do du, we're just going to have negative 1 dx. So if we were doing e to the power of u, we're just going to have negative 1 times e to the negative x. So if this was our du, we had negative e to the negative x dx, and we were supposed to integrate something, let's say v, times e to the negative x dx. That's going to be a lot more work than simply just integrating some integration. Integrating something that's a little bit simpler. So from here, let's do u is equal to x, which means that du is going to be 1 dx or dx. And then v is what we need to find, because we have dv equals e to the negative x dx. Now, this one's going to use u sub e to the negative x dx. The reason we're doing u sub is because negative x is a function inside of a function, so it's input of a function. And again, u sub is just, we have a function inside of a function. We have chain rule. So we make one of those functions equal to a single variable, and then we differentiate with respect to that variable. So a way to think of it is just integrating with respect to the inside function instead of with respect to x, because we already know that the inside function is differentiated with respect to x. So u sub can help us simplify functions by only having a single input to differentiate with respect to. So u equals negative x, which means that du is going to be negative dx. Again, derivative of x is going to be 1. So we have negative, we can pull that out front actually, negative times e to the negative, I keep putting that down. It's going to be e to the u, right? We already said that u is equal to negative x, so e to the u du which is just going to be negative e to the u or negative e to the negative x. Alright, perfect. Well, plus c, but from here, let's just plug in, well, let's write down what we got. Negative e to the negative x, and then, so we have u times v, so negative x to the x times e to the negative x, minus v du. Right, so that's going to be negative e to the negative x with respect to just dx. Alright, so we can just have these become a plus negative x to the x times e to the negative x plus the integral of e to the negative x dx. And since we already showed the work for this, we know that this is just going to be negative x times e to the negative x minus e to the negative x plus c. I would show my work for how we did this integral, but we just showed our work for getting that. And this isn't like a common occurrence or anything, you know. You are going to have to actually show your work for some of your future integrations because we're only working with e, which is a lot more simple to integrate than, say, like some trig functions, which we will get to. It'll be fun. But, yeah, that's one of our answers, and we did get that correct. Oh, speak of the devil, we do have a trigonometric product. So, let's write this down. And, I'll actually save tabular integration for just a little bit. We have the integral of e to the power of x times sine x dx. Now, which of these is going to be easier to differentiate? That's kind of up to debate, you know. Both of these are relatively normal, but actually no, but you could probably use either of these as your u, and you'd get a relatively simple derivative or antiderivative, because again, the derivative of e to the x is just going to be e to the x. And if you know your trig derivatives, these are relatively simple too. It's going to be derivative of sine x is cosine x, and derivative of cosine x is going to be sine x, or negative sine x. So, yeah, I mean, you know, you probably could use either as your u or as your v. I am actually going to use my e to the power of x as a v. Am I? Let's see. Yeah. Well, this one's going to have an interesting way to solve, so I'm actually going to do something interesting in a little bit. But let's write down what we have. We have u is equal to sine x, and then v is just going to be equal to cosine x dx. I mean, not cosine x dx. That's going to be du, right? Differentiating both u with respect to u and then sine x with respect to x. So cosine x dx. And then we're going to have dv is equal to e to the power of x dx, which means that, as we said earlier, if the derivative of x, e to the power of x, is just e to the power of x, then the antiderivative of e to the power of x with respect to x is just going to be e to the power of x. So we're going to have e to the power of x up there. So let's do what we have so far. We have e to the power of x sine x, so uv, minus the integral of v du. So e to the power of x times cosine x dx. Now, as we said, I'm going to do something somewhat interesting. I'm going to have our u be our u be e to the power of x, and then our cosine be dv. I mean, again, these are interchangeable. Cosine x is also relatively simple to differentiate. As we said, that would be negative sine x. I think I did do some proofs for this in my derivatives video, but, you know. And then du is just going to be e to the power of x dx, right? Again, e to the power of x, that derivative is just e to the power of x. And I did write that U very V-like. So D, U. I feel like they should have done, more crazy looking letters like X, or not. I should cut that out. That was embarrassing. No, I was thinking more like A or B. That would probably be easier instead of doing U and V notation, because I feel like, you know, when you're writing, U and V actually look a lot more similar than you'd think. So dV is going to be cosine x dx, and then V is going to be sine x. If we know that the derivative of sine x is cosine x, then the antiderivative of cosine x has to be sine x. And this is going to be more memorization. I honestly think that once you have seen the proofs for why the derivative of sine x and derivative of cosine x are what they are, it's a lot easier to remember them. So I'm like 90% sure that I did do proof for these. But yeah, if proof type learning doesn't help you, then I mean, maybe that wasn't the best, but for me it works. So I don't know why I erased that. We're gonna have to use it right now. So you have e to the power of x minus sine x, not e to the power of x minus sine x. It's gonna be just e to the power of x times sine x minus, let's put this all in parentheses, uv, so e to the power of x sine x minus v du. So this is just going to be minus the integral of v du. So we had sine x with respect to x. It's going to be e to the power of x. Actually, now that I'm looking at this, I don't think this is correct. Let's see. UDV must be du. Yeah, no, something's wrong here. It was hard to tell what I did wrong. Well, yeah, no, I'm not gonna do that correctly. If I continued on that path, it wouldn't be the correct answer. So, I think I'm actually gonna keep our ideas constant. U is gonna be trigonometric, and V is going to be base E. So if U is equal to cosine x dx, U is equal to cosine x, then du is going to be equal to negative sine x dx, and then V is going to equal e to the power of x, and then dV is going to be e to the power of x dx. So u dv, and then v du is what we have. So we're going to have u times v. So that's going to be e to the power of x cosine x. I might need to do some more research on why that method wouldn't have worked. I know that we shouldn't have gotten sine x there, because then e to the power of x times sine x and e to the power of x cosine x wouldn't have worked. Maybe I just did some, very simple mistake, but not sure. But let's just continue doing that. I think, for our purposes, it's probably better to just have u be one type of function, which in this case is going to be trigonometric, and v be another kind of function, which in this case is going to be base e exponential. So we have v du. So yeah, it's not too bad. Yeah, let's do this proof real quick. We have y equals the inverse of tangent. So we can also write that tan y is equal to x. Right, if you take tan of both sides, tan and then tan of this, we're going to have just tan y equals x. I'm going to keep everything around this. This might be a bit of a crushed proof, but it's okay. Tan y equals x. And then from here, we can do some relatively normal like differentiation, implicit differentiation. So we're going to have to do, we have our y's on one side and our x's on the other side. So let's do d dx on both sides. Let's put d dx up there. And now from here, again, this is a function of y that you have to differentiate with respect to x. So you're going to have to do d dy of tan y times dy dx. I've actually talked about implicit differentiation in a separate video, and I explained why this needs to be out here. Essentially, when you're implicitly differentiating, you have to understand chain rule. And if y is a function of x, that means that y uses x as an input, so you can differentiate with respect to y and then multiply that by derivative of x. So yeah, actually it's more like y is going to be the input, so you have to differentiate with y and then you have to multiply by the derivative with respect to the input of y, which again, y is going to be defined as a function of x. And then we have d dx of x, which is just going to be 1. So d dy of tan y, we actually did this. It's not really a proof, it's more just a worked example, but it's just quotient rule, sine x over cosine x, and you would get secant squared. So we have d dy, or, well, maybe for this one it'd probably be easier to just have it as 1 over cosine squared. Not d dy, it's going to be just dy dx. Dy dx times 1 over cosine squared x is equal to 1, and then when you divide both sides by 1 over cosine squared, 1 over 1 over cosine squared is just going to be cosine squared. So we have dy dx is equal to, it's not cosine squared x because we differentiate with respect to y. It's going to be cosine squared y. So we have dy dx is equal to cosine squared y. And then from here, we want to find the derivative of a function of x, not a function of y. So we have, if y was equal to arctan x at the very beginning, we have cosine squared of arctan x, which can be simplified quite a bit, right? This one requires some creative thinking. I think I did a different proof for y arctan. That derivative is 1 over 1 plus x squared in my other advanced derivatives video, but this one, I found this proof a little while ago and I thought it was rather interesting. We can write this as a triangle. If we have y is going to be our angle, then tangent of y has to be x over 1, right? Because if arctan, well, I've been using inverse of tangent, so I'm going to continue using inverse of tangent. If inverse of tangent x is equal to y, then tan of y has to equal x, right, as we said, and tan is just opposite over adjacent. So we have our opposite, x over something equals x, and that something has to be 1. So we have x over 1, and then from there, we just simply get the Pythagorean theorem. We have to do 1 squared plus x squared has to equal c squared. So we have, let's write that out. We have 1 squared plus x squared equals c squared. So I'm just going to say this out loud. We have 1 and x squared equals c squared. So you have to do the square root. And this isn't going to be plus or minus. This is just going to be plus because, again, geometry has to be positive. Well, for now it does. So we have the square root of 1 plus x squared. And then from here, it's starting to look rather similar to what we want to see, right? So cosine of y, or, adjacent over, let's write down 1 plus x squared. We have cosine of y is equal to square root of 1 plus x squared. And we have cosine squared y, right? We have cosine squared y, so we're going to have to square this, and we just get cosine squared or this is going to be 1 over 1 plus x squared, right? This is adjacent over opposite, adjacent over hypotenuse, so we have cosine squared y is equal to 1 over 1 plus x squared. And now we just get dy dx is equal to 1 over 1 plus x squared. We did dy dx is equal to cosine squared over here, right? 1 over 1 over cosine squared is just going to be cosine squared. So we have cosine squared y over here, and we had cosine squared y over here. So dy dx has to be 1 over 1 plus x squared when y equals arctan x. Might be a bit of a weird looking proof. I thought it was interesting. Like, it's definitely creative. That's like a given. But it's definitely unique. Now, let's do some stuff. Where was my original tab? Okay, there we go. And, yeah, let's write down what we have. Now, from here, we have, well, let's plug in everything that we have. We have uv is equal to x times inverse tan x. So minus integral of v with respect to u. So x times 1 over 1 plus x squared with respect to x. So now we can simplify this just a little bit. We can have that x over 1 plus x squared. And now this looks like it's an intimidating function, I won't lie. But this one I think is okay. This one we're going to have to use u sub, right? Because we can't undo quotient rule. That's just not allowed, at least to my knowledge. Maybe there's some super obscure way to undo quotient rule, but we can't undo quotient rule when we integrate. We have to use chain rule. And automatically I see that 1 plus x squared is a function at the bottom of something. ln is the derivative in which you get a quotient. You get 1 over x when you differentiate ln x. So if we have u equals x squared plus 1, maybe, just maybe, we'll try and then we'll see if it works or not. If we try u equals x squared plus 1 and we have, a nice and easy derivative, we'll have 1 over u by the end of it, which we know the antiderivative of 1 over x is ln x, so the antiderivative of 1 over u is going to be ln u. So let's write that out. We have u equals 1 plus x squared. So let's differentiate with respect to x. So du dx is equal to 2x. So we can simply multiply. Du is equal to 2x dx. And we'll solve for dx. So we're just going to put that 2x back down. We have dx is equal to du over 2x. And then from here, let's rewrite what we had. We had dx is equal to, dx is equal to 1 over 2x, right? So du over 2x. And then this is just going to be u. So x and x, those cancel, and we're left with 1/2 times 1 over u with respect to u, which again we said was ln u, so we have 1/2 times ln u, so we are left with just 1/2 times ln x squared plus 1. And then plus c. Alright, that is one of our answers. They don't have parentheses, they don't have absolute value bars. I think that's probably just because x squared plus 1 is always going to be positive. Whenever you square any value, unless it's imaginary, you are going to get a positive value, and then plus 1, so you're going to get a positive value there as well. But, yep, that is one of our answers. Let's see if it's correct. And it is. Alright, next one. Okay, this one's interesting. Let's write what we have. We have e to the power of x cosine 2x. And after this, I think, well, this might need to do. We'll see what this needs. We have e to the power of, oops, wrong thing. We have e to the power of 2x, not e to the power of 2x, e to the power of x times cosine 2x. Alright, I'm going to make v be our, dv be e to the power of x dx, which again we said the integral of e to the power of x is e to the power of x because the derivative of e to the power of x is e to the power of x. And then du has to be found, so u is equal to cosine 2x. And then using chain rule, if u is equal to 2x, I know we're using a lot of u's and v's, which is why, again, I don't really like this notation too much, but f and g gets a little bit confusing for me. So du is equal to 2, or u prime is equal to 2, so we have to do u prime times cosine u prime, so we're left with 2 times negative 2 sine u, which is, again, 2x. So negative sine 2x dx is what our du is going to be. I feel like I might have actually confused somebody a little bit, but du is equal to negative 2 sine 2x dx. I'm actually just kind of skipping a step right here. We're differentiating u, right? U with respect to x. So this is actually going to be du over dx, or du with respect to dx. And then I just multiplied the dx to the other side. If that wasn't obvious, I'm sorry. I feel like I didn't actually say it out loud, but yeah. And then from here, let's write what we have. We have uv, so e to the power of x times cosine 2x minus v du. So we have e to the power of x times negative 2 sine 2x, which we're just going to put that negative out there, 2 sine 2x dx. Alright, from here, let's do some stuff. We have, let's let u be 2 sine 2x, and then again we'll have to use chain rule, so u is equal to 2x, we have a function inside of a function, u prime is equal to 2, so we have 2 times 2 times sine u's derivative, so that's going to be cosine u, and if u is equal to 2x, we have 4 cosine 2x. Alright, fantastic. And then we have, so let's write that down. We have du dx is going to be 4 cosine 2x, so du is going to be just 4 cosine 2x dx. And then from here we have v equals e to the power of x, and then dv is equal to e to the power of x dx. Technically dv we had first, but, you know, derivative, antiderivative of e to the power of x is just e to the power of x, so I didn't think we needed to go over that. And then from here, we just plug in again. We have e to the power of x cosine 2x plus e to the power of x, so uv, not going to look like that's going to be plus 2 times e to the power of x sine 2x, and then this is going to be minus v du, so e to the power of x, I'm actually going to bring that 4 right out using our constant rule. If we multiply this and this, we should just be able to bring out that 4 because this will all be in the same term. E to the power of x cosine 2x dx. And we could continue doing this, but again, remember we are integrating e to the power of x cosine 2x. So if we have the two being the same, we can write this as I equals, I didn't need to erase that, we're going to write this as I equals this, which means that we can put I over here, minus 4I. So if all of this equals I, so let's write what we have. The integral that we are supposed to do is going to be, what was it? It's going to be integral of x cubed e to the power of x dx. Now, let's just think about using normal integration by parts. We could say that, e to the power of x is easy to differentiate. Integrate, so we're just going to have dv be e to the power of x dx. So v equals e to the power of x. And then we have u is equal to x to the power of 3. So du dx is going to be, well, you bring that 3 out, and you do 3 minus 1, which is 2, so you're left with 3x squared. So du is equal to 3x squared dx, because du dx is equal to 3x squared. And then from here, we could just continue plugging uv minus v du. But it might just get a little bit tedious to constantly have to rewrite our steps. So for this, we use something called tabular integration. It's not wrong or anything. Let's write down what we have. So u dv is equal to uv minus the integral of v with respect to u. So this is plus uv minus v du. And if you continue cycling through integration by parts, you're always going to have plus, minus, and then plus, minus, and then on and on. So we're going to have this oscillating plus, minus, plus, minus. And then from here, we differentiate u, and we integrate v. Now, let's kind of talk about why this works. So, let me do it real quick. When we have u, we're going to have to differentiate u. So, which one of these is easier to differentiate? Arguably, it's e to the power of x, but e to the power of x is definitely much easier to integrate than x to the power of 3. So we're going to have x cubed be in here, and so when we differentiate, we get 3x squared, and then when we differentiate that, we get 2 out. And so when we bring that 2 out and multiply it by 3, we're going to have 6 times x to the 2 minus 1, so 6x. And then again, derivative of x is just 1, so we're left with 6. And actually, we are going to need another column. We want to differentiate u until we get to the point where u cannot be further differentiated. So I'm just going to kind of continue our table. Du sines u and then v. Again, those u's and v's look very similar. I'm going to do this. I don't like that. I'm just going to put u, a little bit more obvious, u and then v. And then 6 can be differentiated further, so we'll get 0. So the point of differentiating u until you can't any further is so that you get to 0. And that will be a good segue into some functions where this will not be the most correct way to handle it. And then v is going to be e to the power of x, integral or antiderivative of e to the power of x is e to the power of x, antiderivative of e to the power of x is e to the power of x, and then on and on. And you could go further, but since u stopped here, v will stop here. You can't differentiate 0 any further than 0, so you can't differentiate e to the power of x further. And this is going to be plus. If we have that plus minus oscillating, plus is going to be our last one. And then from here, we did uv, right? So we're going to have to multiply u and v. So uv, so we're going to have plus, right, plus uv, so plus uv. If this is dv, you can think of this as dv. We went to v down here, and then we went to v1, and then v2. You know, we just kept on integrating further and further. But if this is dv, we do not multiply across. We multiply across this diagonal, so that if this is v, we're doing u times v, right? And then this is going to be plus uv minus v du. So minus this times this, plus this times this, minus 6 times e to the power of x. And then, you know, you could have an e to the power of x down here, and then do plus 0 times e to the power of x, but I don't think it's really necessary to show that 0 times anything is 0. So we simply stop at that 6 times e to the x. So we're left with, let's multiply across. We had plus x cubed, not the correct one. We have plus x cubed times e to the power of x, so yeah, we'll write that as x cubed e to the power of x, and then minus 3x squared e to the power of x, plus 6x e to the power of x, minus 6 e to the power of x. We'll put that over there. And yeah, the reason that this works, again, is we have a u and we have a v. This v has to be relatively simple to integrate, so that this method works best. And then u has to be easy to differentiate. And once you differentiate to the point where you can't differentiate any further, or once you differentiate to the power of 0, you simply just multiply across and down 1. If u, v, and is what you have, then the term directly above v has to be dv, right? If this is dv, then this has to be v, so you're going to multiply it across that diagonal. And if this is the dv for another integration by parts, this is going to be v. And if this is the dv for another integration by parts, it's always going to be v is directly one below. So we have to multiply on this diagonal. The signs are oscillating because the signs oscillated for this one. We have a plus up here and a minus over here. So it's going to be plus, minus, plus, minus, plus, minus when you do this method. And then, again, we have to differentiate u so that we get du, so that this is possible. And, yeah, I mean, I tend to, like, go for more proof-based, like, ideas of why things work. So this more, like, common sense approach, while I do understand why it works, it just doesn't do it for me. And, I mean, I just prefer integration by parts, but I'm also a bit weird in that I prefer systems of equations when I'm doing, what's it called, partial fraction decomposition, which I have yet to talk about. And, real quick, I'm not actually going to solve any example because I feel like we're running a little bit over what I wanted this video to be, like, in terms of length. The reason that I don't like tabular method for certain integration problems is because what if you have a sine and cosine type thing, right? I'm not going to come up with a problem, but if you have a u sine x, or u any trig function, you will never get to 0. You will always just go cosine x minus sine x minus cosine x sine x, and you will always go that way. Perhaps you might be able to integrate, but it can get messy very quickly. I just tend to say that when you have a trig, like a product of a trig function and another function, it's almost always going to be easier to just do integration by parts, and then do that thing where we set I equal to something at the very beginning, and then solve for I. That's most likely what your trig functions are going to look like, because, again, this cycle will continue forever. U will never reach 0. And dv, like if you continue integrating this, it'll also never reach 0. Unless you have a u or a v that reaches 0, this might be, this might be fine, But there are certain examples of like equations where this doesn't work. Well, in tabular integration doesn't work as best as it can for other functions. But well, so if you have a u that goes straight to 0, if you have like a really nice like x squared or something that goes 2x, 2, and then 0, and you have, say, sine x here, then you have integral of sine x is going to be negative cosine x, and then integral of negative cosine x is negative sine x, and then integral of negative sine x is going to be cosine x. There might be something to doing it this way, to have this, and then plus minus, plus minus. And that might be, well, it's probably a little bit easier. But if you have, say, like an e to the power of x or some ln x or something, it'll be very ugly very quickly. Like, if you have e to the power of x, e to the power of x, e to the power of x, I'm using a relatively simple one, this will never stop, and this will never stop. V will never stop, and u will never stop. So, just as a reminder, if you have two functions where either of them oscillate or continue to cycle into derivative and integral, then it might be easier to just do integration by parts. But there might be a way. You could just say that, like, at a certain point, like if this is plus minus minus plus minus, you could say that at this point where you get to e to the power of x minus sine x, that you can stop because you were trying to integrate e to the power of x sine x. But that might be a little bit too much, I think we're getting a little bit too into it, because at that point you're going to have to, really pay attention to what you're doing, which is not going to be easy when you're under time pressure, even when you're like doing this and you're just stuck. But yeah, tabular integration, it's definitely valid. It works. The math behind it is solid, but I personally dislike it because I don't understand it as well as I do integration by parts in the normal way. And so, yeah, I might do some more practice of integration by parts, but for now I think we're just going to go straight into partial fraction decomposition. Now, that's a big word for something that's not too, I wouldn't say it's easy or anything, but it's not too complex. So, let's have a random value. I'll just come up with something. We'll have 2x plus 7 over x squared plus 9x plus 8. How are we going to simplify this? We really can't. 2x plus 7 doesn't have anything in common with these factors, so we can't, get into a 1 over something, let's call it u, 1 over something situation where we can actually integrate with respect to u and then get a nice and simple ln u. That's not going to work. What we're going to need to do is have a decomposition of these terms. So let's factor 2x plus 7 over x squared plus 9x plus 8. At this point, I think if you have been following most of this video and most of my other videos, I think you can probably factor this in your head, but it doesn't hurt. We have AC, or let's write down what we have. We have, if this is ax squared plus bx plus c, we have a equals 1, b equals 9, and then c equals 8. You could do the grouping method for this, it doesn't matter if that's how it works for you, but I like the guess and check method. We have AC is equal to 1 times 8, so 8, and then what are the factors of 8 that add up to 9? There's 2 and 4, but there's also 1 and 8, which is what we're going to have, 1 and 8, so we have x plus 1 times x plus 8 to get x squared plus 9x plus 8. And so from here, let's write down what we have. We have 2x plus 7 over x squared plus 9x plus 8, so x plus 1 times x plus 8. Alright, I am going to solve this the way that I was taught, but then I'm also going to solve this in a way that is more beneficial for a slightly more complex function. So this is a product of two factors, right? Linear factors, and we have a linear factor in our numerator. So we can simply split this into two fractions, right? If we had, like, say, we had an a over x plus 1 plus a b over x plus 8, when we multiply it, we should be able to get some, not when we multiply, when we add those two fractions, we should get a end fraction that has these two multiplied. Remember, when you do fraction addition, you have to have a common denominator. So once we have that common denominator, we should just get 2x plus 7 over x plus 1 over x plus 8, which is what we want. We need to split this into two fractions so that these will be easier to integrate. And now from here, let's do this real quick. We have a over x plus 1 is plus b over x plus 8. Now from here, we have to have a common denominator. So this will be multiplied by x plus 8, and this will be multiplied by x plus 1. So we get x plus 8 times x plus 1 over there, right? Anything that we have to do to the numerator, we have to do to the denominator as well, and vice versa. So we have to multiply that by x plus 1 and that by x plus 8. And since we have a common denominator, we can simply strike all of them out, and we're going to be left with a times x plus 1, a times x plus 8 plus b times x plus 1 equals 2x plus 7. A times, let me write that up, a times x plus 8 plus b times x plus 1 equals 2x plus 7. Now let's distribute our a's. We have ax plus 8a plus bx plus b equals 2x plus 7. And so what do we have attached to our x's? We have a, we have b, and we have a2. So we can have a plus b equals 2. I'm going to rewrite this. And then we have 8. What do we have attached to, like, a constant? We have b is a constant, 8a is a constant, and 7 is a constant. So we're going to have 8a plus b equals 7. So let's do that real quick. Since this is a system of equations, we can simply subtract one expression, I don't know, one expression by the other, and when we subtract them, we're just going to get negative 7a equals negative 5. So once we divide negative 7a and negative 5 by 7, we get, or by negative 7, we're going to have a equals positive 5 over 7. Then from here, we are going to do b. So if a plus b is equal to 2, then 2 minus 5 over 7 is what we're looking for, and that's going to be 1 and 2 over 7, or 9 over 7. And then from here, well, we could put 9 over 7, well, let's write down what we had originally. We had 5 over 7 times, wait, what did I use for what? Okay, yeah, we had, yeah, okay, so we had a, b over x plus 1, and then b over x plus 8. And it's very important that you know which one is which. I just have been erasing and rewriting my work, so it's a little bit more troublesome to remember. And while you could put 5 over 7 in this numerator, and then, bring that 7 down there, and then distribute the 7, and then try to integrate it like that, I think it's much simpler to think of a over x plus 7. If you have a fraction as your a, you just have 5 over 7 times 1 over x plus 1. I think that this is a lot easier to integrate. And then this is going to be plus b over x plus 8, which we said was 9 over 7. So 9 over 7 times 1 over x plus 8. And we are going to try and integrate all of this with respect to x. So we're going to integrate this with respect to x, and we're going to integrate this with respect to x. And then from here, 9 over 7 and 5 over 7, while they are fractions, they are also constants. So we can pull them out. We'll have 5 over 7 times the integral of 1 over x plus 1 dx, and then plus the 9 over 7 times the integral of 1 over x plus 8 with respect to x. And from here, we simply do some nice ln integration. This is going to use u sub, but honestly, I don't think u sub is too important for this part. I mean, at a certain point, you'll just kind of see where it will go, but I mean, it doesn't hurt. So we have u is equal to x plus 1. So derivative of u is going to be, derivative of x is always going to be 1, derivative of a constant is 0. So 1 times dx, du equals dx. And then we can do both of these at the same time, just to prove how great of a mathematician we all are. We have du is equal to derivative of x. Let's make this v, so it's a little bit easier. dv, and then derivative of x is 1 times dx, so dv equals dx. And then we're going to have 1 over u du plus 1 over v dv. And again, we know how to integrate 1 over v, or 1 over x, or 1 over u, and that's just going to be ln. So we're going to have 5 over 7 ln absolute value of u, which is x plus 1, plus absolute value, 9 over 7 times ln of absolute value of v, which is x plus 8 plus c. So yeah, that was like a systems of equation worked example of what's it called? Partial fraction decomposition. But there is systems of equation isn't always going to work. There is going to be a slightly more interesting way of doing it. I mean, I see how it works, and it definitely does make sense. It's not like crazy or anything, but if I can use systems of equations, I will use system of equations because I like it a little bit more. But this is what you are going to have to do if system of equations doesn't work. System of equations only works when you have a something attached to an x, like if that's something, plus a constant. So once you add like these, then if you have a form where you have this times x plus a constant equals this times x plus a constant, then you just set all of the coefficients of x equal to one another, and then all of the constants equal to one another. I don't know why I use 7 when I've just been using blanks for everything else. But yeah, it only works if it's written like that. But let's say we have a more strange looking function. We're actually going to do a nice 2-for-1 deal and do something where you have a, well, let's just do it. We have x squared plus 1 over x times x minus 1 cubed. And we're going to have to integrate this with respect to x. Now, x squared plus 1 and x minus 1 have nothing in common. You can't factor x squared plus 1, and even if you could, you cannot cancel it out with x minus 1 cubed. And you can also, for that matter, not cancel it out with x. So from here, we're going to have to do partial fraction decomposition. And you might be thinking, okay, we'll just have a over x plus b over x minus 1 cubed. And we'll be like, let's just do it. But that's not going to work. When you have these, you have to include several different things. X minus 1 is repeated 3 times, right? You have x minus 1 cubed. So there are going to be several different factors. We're going to have a over x plus b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. And all of this is going to be equal to x squared plus 1 over x minus 1 cubed times x. And then from here, we need to multiply all of these to get this. Like, we'd have a times x minus 1 cubed plus b times x minus 1 squared plus c times x minus 1 plus d times x. I'm just trying to get all of these to be the same. Like, when you multiply x, you have to multiply by x minus 1 cubed to get x times x minus 1 cubed. When you multiply x minus 1, you have to multiply by x minus 1 squared to get x minus 1 cubed, and you also have to multiply by x to get that x in the front. X minus 1 squared, you have to multiply by x minus 1 to get x minus 1 cubed, times x still, and x minus 1 cubed, you don't have to do anything to get x minus 1 cubed, you just have to multiply by x. And this is all going to be equal to x squared plus 1, or the numerator that we were working with. So we have to get some of these to equal 0. So the methodology behind this is, if you can get some of these factors, all of these factors have something in common, right? Well, most of these factors. A, B, and C all have x minus 1 in common. And, B, C, and D all have x in common, right? X, x, x. So if we want to get our A, B, and C, and D all away from one another, we're going to have to plug in 1 and 0 so that we get 0 factors. And let's do that. 1 minus 1 cubed plus B times 1 times 1 minus 1 squared plus C times 1 times 1 minus 1 plus D times 1. Alright, and that's equal to 1 squared plus 1. Anything that you have to do to the other side, which in this case was substitute x for 1, you have to do to the other side. I mean, anything you do to one side, you have to do to the other side. So if we substituted 1 on one side, we have to substitute 1 on the other side. And we substituted 1 in particular so that we can get this d by itself, because x minus 1 is not one of its multiples. So let's plug in 1 for all of these. 1 minus 1 cubed is going to be 0. 1 minus 1 squared is going to be 0, so 0 times b, and 0 times a. Both of those are 0. 1 minus 1 is 0, so 0 times c is 0. And then so we're left with d equals 2. Alright, perfect. So we have d equals 2, because d times 1 is d. 1 squared plus 1 is 2. So we have d equals 2. And then let's do 1. Let's plug in 1. We have, not 1, we have to plug in 0 so that we get this by itself. 0, 0, 0. And then we also have to plug in 0 here. So I'm just going to kind of say out loud, we have a times 0 minus 1 cubed, and then plus b times 0 times x minus, or 0 minus 1 squared. But once we said that we have b times 0, that's going to be 0, and plus c times 0 minus 1, so 0, plus d times 0, 0, equals 0 squared plus 1. And now when we plug in 0 minus 1, we get negative 1. Negative 1 cubed is negative 1. So we have negative a is equal to positive 1, so we have a equals negative 1. Alright? And then from here, let's reevaluate. We're going to have to do something a little bit weird now. We have a and d, but there's no simple way to get b and c. The reason I chose this problem in particular is because there will be, places where you have x minus 2 and x minus 3, and it would be a lot simpler to solve for b, c, and d because the other ones will always cancel when you multiply by non-repeated factors. But when you do have repeated factors, you're going to have to go back to our systems method. So we have, let's write down what we had. We said that a is equal to negative 1, right? Yep. A is equal to negative 1, and we said that d is going to be equal to, what do we say d was equal to? D was going to be equal to 1, oh, d is equal to 2. So we have, yeah, that's right, right? Yep, d is equal to 2, because you do d times 1, and then 1 squared plus 1, so d times 1 is d, equals 1 plus 1, which is 2. So d equals 2, and then from here, we have to do some kinda tedious math, but it's definitely useful math. So let's plug in our negative 1 and our 2 for our d's. So we have 2d plus 2d, not plus 2d, what am I saying? It's going to be plus 2x because when you do that d over x minus 1 cubed and then you get that x onto it, you have dx, and then we plugged in d, so plus 2x, and then minus 1 in front of that x minus 1 cubed. Then from here, let's plug in some random values. We could, we just want to get a system of equations because now we only have two variables. We only have b and c. So we can go back to our systems of equation method to get those b and c's when we have like values plugged in. And it'll make sense in just a second. So we could, plug in 7, 8, and crazier numbers, but we have cubes and we have squares. This is going to be a lot more difficult to calculate. As a general rule, I think it's a lot easier to have things close to what you, like maybe 2 or 3 within the range of your original values. If we have negative 1 and 2, I would prefer if we kept our numbers also very small. So let's plug in negative 1. Let's do negative 1 times negative 1 minus 1 cubed plus negative 1 times b times negative 1 minus 1 squared plus c times negative 1 times negative 1 minus 1 plus 2 times negative 1 is equal to negative 1 squared plus 1. And that's just going to be, well, negative 2, minus 1 minus 1. So negative 2 cubed is negative 8 times negative 1 is going to be positive 8 plus negative 1 times b. So negative 1 minus 1 is negative 2. Squared is going to be positive 4 times negative 1. So negative 4b. And then negative 1 minus, 1 is going to be negative 2 times negative 1 is plus 2. C and minus 2 is equal to 2, right? And then from here, we'll just get, let's bring that 8 and that 2 to the other side. So we're going to have, let's think, no, we're good. We're going to have 2 plus 2 minus 8, so negative, or 2 plus 2, 4, minus 8, so positive 4. So minus 4b plus 2c is equal to 2 plus 2 minus 8, negative 4. Then we'll just divide everything by 2. So we're going to have, or by negative 2, so that we can get this pesky minus out the way. Minus 2b, 2b minus c is equal to negative 4 divided by negative 2 is going to be positive 2. Alright, let's also write that somewhere. In your work, you probably don't need to write this out, but 2b minus c equals 2. I just need to erase this. Let's also plug in another relatively small value. We have a negative 1 out there. And this isn't technically like minuscule or anything, but we already plugged in negative 1, 0, and 1. We could go negative 2, but I see immediately that negative 2 minus 1 is negative 3, and we're going to cube that, so we're going to get some relatively large values you don't want to work with. Since we have x minus 1 in all of these, 2 minus 1 is equal to 1. So it'll be relatively okay if we plugged in x equals 2. So we have negative 2 minus 1, so cubed, plus b times 2 minus 1, plus c times 2 minus 1. Oh, this is 2 minus 1 squared. C times 2 minus 1 plus 2 times 2 is equal to 2 squared plus 1. Alright, and then again, 2 minus 1 is 1, so 1 cubed is negative 1, plus 2 minus 1 squared is 1, so plus 2b, plus 2 minus 1 is still 1, so 2c, plus 4, 2 times 2 is 4, plus 2 squared, 4 plus 1, 5. Alright, perfect. Now we simply solve, well, not solve for anything, we just need to get our numbers on one side and our other stuff on the other side. So we have 2b plus 2c is going to equal 5 minus 4. When we bring that, it'll be negative, and then minus 1 when we bring that, it'll be positive. So we're going to have 5 minus 4 plus 1, so 1 plus 1 is going to be equal to 2, and then we are going to have b plus c equals 2 when we, divide everything by 2. 2b, 2c, 2, all of them have 2 in common, so we can simplify that a little bit, and from here, we can finally get sort of close to actually finishing this. We still have quite a bit of work to do after this, but we're getting there. We have b plus c equals 2, and we have minus c and we have plus c, so we can add both of those, and we'll get 3b, well, wait, what? Oh, it's not 2, b plus c equals 2. I forgot, it's going to be b plus c equals 1, because 2 divided by 2 is 1. And then b plus c is equal to 1, and then when we add, we get 2b plus b minus c plus c, and then 2 plus 1. So we're going to have 3b equals 3, so b equals 1, and then if we have b plus c equals 1, c has to equal 0. So now, let's plug in everything we had. We had negative 1 over x, a over x, plus b over x minus 1, so 1 over x minus 1, plus c, which is 0 over x minus 1 squared. 0 divided by anything is 0, so I'm not going to write that down. And then d over x minus 1 cubed, d is equal to 2, so we have 2 over x minus 1 cubed. Alright, and this is all integrated with respect to x. Now, this one is going to be such annoying to have to differentiate, to integrate. But we can definitely do it. Now, let's see. Integral of negative, well, let's just split these into factors. We have, not factors, into terms. We can bring that negative out. We have 1 over x dx plus 1 over x minus 1 dx. 1 over x plus 1, and 1 over x minus 1 dx plus 2 over x minus 1 cubed dx. Now, at this point, you might be ruining the day that you ever learned calculus, because you might think that we have to do partial fraction decomposition for this one, but this one is going to be a nice and easy u sub, well, easy in quotation marks. The integral of the integral of 1 over x dx is going to be ln x, and the negative is just out there, because negative is just negative 1, which is a constant. So we have negative ln, absolute value of x, plus, we can do u sub for x minus 1, but I think you picked up on that pattern. If we have a x in the denominator, that's just by itself, and we have du equals dx. Once we do 1 over u and integrate 1 over u with respect to u, we're just going to have ln of u, which is going to be x minus 1. So when you have these kinds of like problems where you have 1 over x minus 1 or 1 over x plus 8, it's just going to be ln of x plus 8, ln of x minus 1, ln of whatever thing you have is just 1 over x plus or minus something, you know? And then from here, we can do our u sub, right? 2x minus 1 cubed. So 2x minus 1 cubed. We have a function inside of a function, and we cannot do quotient. We cannot undo quotient rule. So we're having x minus 1 cubed. I'm just going to write u is equal to x minus 1. We'll do du is equal to dx. Again, derivative of x is 1, so 1 dx, but we have 2 over u cubed is equal to, not is equal to, du, integrate, and then I'm just going to write this as 2 times u to the negative 3 du, which, let's do that 1 over n plus 1 thing. We have 1 over n plus 1, n is going to be negative 3, so 1 over negative 3 plus 1 times 2, so I'm actually going to put that in the numerator, times u to the negative 2, or u to the negative 3 plus 1. I'll even write that down. Negative 3 plus 1 plus c, and so we'll just do this in our heads. We have negative 3 plus 1, which is negative 2, and we have 2. So 2 divided by negative 2 is negative 1. So we're going to have negative out in the front, and then negative 3 plus 1 is negative 2. So u to the negative 2 is going to be 1 over u squared. We said that u was x minus 1, so we're going to be left with 1 over x minus 1 squared, and then plus c. So our final answer is just going to be 1 over x minus 1 squared plus c. So yeah, that was a lot of work. There might be a way to optimize that work, make it a little bit easier, but you know, I'm hoping, I did go relatively quickly through that, but I'm hoping that we saw what we needed to do. We had repeated roots in our denominator, right? So we had to set several different fractions, not just a over x and a over x minus 1 cubed, otherwise we would just never have gotten this factor at all. Not this factor, this term. I keep using the wrong thing. I'm using pen. Okay. So if we had just done a over x and b over x minus 1 cubed, we wouldn't have accounted for x minus 1 or x minus 1 squared, which are definitely factors of the denominator. So we'd have to split it into repeated roots of the same thing, and then from there we had to plug in numbers that could cancel out the rest of the roots so that we get some of those values accounted for. But since we were left with 2 variables at the end, we had to do 2 equations in our system of equations so that we can solve for those 2 variables. So we just plugged in values that were relatively close to the original values that we plugged in. Since we only had to plug in 0 and 1 for this one, we plugged in negative 1 and 2, values that are also pretty close to 0 and 1. And then from there, we had 2 systems. Now, God forbid, if you have more than 3 or 4 factors in your denominator, if this was x minus 1 to the power of 4, then you would have e over x minus 1 to the power of 4 as another fraction in your decomposition. And if you had to solve for e, you'd have to do 3. So a good way to think of this, the number of variables that you need to solve for is the number of equations that you're going to have. So if you had 2 variables, like we did, b and c, we had to plug in 2 different values to get 2 different equations. Now, if we had 3 values, b, c, and e, per se, then we might have to have 3 equations. And if we had 4 values, we'd have 4 equations, and on. And I'm hoping that this system of equations work does come back to you from, previous education in algebra. But yeah, it's going to be quite the challenge if you have more than like 3 variables. But 3 equations, 3 variables is relatively doable. And yeah, I mean, that's probably the extent of partial fraction decomposition for most high school calculus students. You have to account for every single root, regardless of how many times it's repeated, and you plug in values that cancel out the other roots, and if you are left with variables that are not canceled out, then you have to create a system of equations where you have the same number of equations as the same number of variables that you need to find out, and then you integrate whatever is left. And yeah, that's gonna be kind of it for partial fraction decomposition. If it's confusing, I can do more examples, but I think if you can understand most of what we were doing right then, I think you're probably going to be fine for partial fraction decomposition. I think that the first question that we did, that 2x plus 7 over x squared plus 9x plus 8, is probably a little bit closer to what you're going to have to do in calculus. And then let's, what did I say I was going to do after? Improper integrals. Okay. And we're also going to very, very briefly touch on multiple integrals, double integrals, triple integrals. That will get into multivariate calculus, but, I think we can do a couple of questions, maybe like challenge questions, like you can watch it and follow along if you'd like, but if it's, something that you don't really, understand, that's perfectly fine. You don't have to understand it. We're strictly talking about univariate calculus beforehand, so randomly switching to multivariate is going to be not the greatest decision of mine, but I think certain multiple integrals are okay to understand. I'm gonna do some very basic ones, like constants and yeah. I think you guys can handle it, but let's do improper integrals. Now, an improper integral. Let me just kind of write a definition. An improper Okay, well, an improper integral is just when you have I wouldn't say impossible, interval of values, but we know that it's a definite integral. So let's write down what our original idea of a definite integral is. It's the integral from a to b of f of x dx. Now, this is considered improper if you have the limit as some value approaches infinity, right? If you had a to infinity, this is considered an abuse of notation because, a and b have to be finite, but you'll probably see values written like this from a to infinity of f of x dx. And I actually kind of spoiled what we're going to have to do to solve improper integrals, but this is let's say we had some kind of a graph that, does a squiggle. It's not going to look like that, but if we are doing the integral from, say, a, we'll put that down here, and then all the way to infinity, we would have an infinite area under the curve, right? Which isn't possible. I mean, it's possible, but it's not going to be particularly helpful for us. It's not going to, be calculatable. So, that's not a word, but whatever. If you have this integral from a to infinity, this is also the same as the integral of a to b, or b is approaching infinity, and you're solving the limit, right? And that's going to be how we are solving these improper integrals. Improper integrals are just definite integrals where you are trying to find the limit as that definite integral approaches infinity, or one of the endpoints of that interval is approaching infinity. It could actually be, it doesn't have to be infinity, I don't think. It could be just has to be something that's not calculatable. There are improper integrals where you're not going to be using infinity, but There's also some kinds of improper integrals where you are taking the limit as one of the endpoints approaches another value. So if you have the limit as c approaches b of the integral from a to c of f of x dx, and you could swap a and b and c, but it doesn't matter as long as you know that if one of the endpoints is approaching another value, if the endpoint is changing, that's considered improper, because how are you going to calculate the area under the curve, right? Well, we kind of, spoiled it. This is going to be how you're going to solve it. You have to do the definite integral that you can do, and then try to do the limit as that approaches another value. But this is going to be a lot more of what we're doing. The limit as, say, b approaches infinity of the definite integral from a to b of f of x dx. Yeah, I mean, it sounds crazy, but I think it makes sense. Let's do a function that you've probably seen before. Let's say we have this 2 to the power of x over infinity, and not 2 to the power of x over infinity, but if you have this area where, it's approaching, it's not actually 2 to the power of x, it's just a function where x will just continue going onwards to infinity, you'll have to set infinity to some value. In this case, we used b because we wanted it to look like our original definition of a definite integral. But it might be t. That's what some people use. But it doesn't matter too much. You're just gonna have to solve this definite integral normally. Keep t as t. So when you have to plug in values, when you have that f of b minus f of a, big F, your a will be a number, but your f of b will just be a function of b, and then you solve that function of b's limit as b approaches infinity. Making this sound a little bit more complicated than it actually is, but let's do a relatively simple one. We're going to have the integral as, I'm not sure if I'm going to use t or not. I mean, some people use t, but it doesn't matter too much. We'll use b. Let's keep it in the same notation as our definite integral, so it's a little bit, more natural. We have the integral from 1 to infinity of 1 over x squared. Alright. Now, well, it's not equal to 1 over x squared. I don't know why I wrote that. It's going to be the integral from 1 to infinity of 1 of x squared dx. And in case you haven't seen this graph, it's always going to be positive because x squared needs to be positive. And it's going to be like that. It's kind of hard to, illustrate. But as you can see, this seems relatively finite, Maybe not super finite or anything, but if you have this value that gets closer and closer to the y-axis, and this value that gets closer and closer to the x-axis, even though it will continue increasing forever, it will get very, very close to 0. So close to 0 that at a certain point it won't even matter. And just in case that's kind of not translating very well, it's like if you plug in infinity into x squared, 1 over infinity is 0, right? So if you do the limit as x approaches infinity of 1 over x squared, you are going to get 0. And we are going to have a very interesting value for what our integral is going to look like. So let's do this. This is also can be written as the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx, right? Now, this is relatively normal, right? We had direct substitution to get that b from infinity. And so when we do that, we have the limit as b approaches infinity of the integral from 1 to b of x to the negative 2. Let's do our 1 over n plus 1, so 1 over negative 2 plus 1, x to the negative 2 plus 1. We're going to have negative, well, negative 2 plus 1 is negative 1, so 1 over negative 1 is negative 1. And then negative 2 plus 1 is negative 1, so we have x to the negative 1, so negative 1 over x. And then that's going to be it. Yep, we're going to have negative 1 over x. And then we will just plug this in to our value. We have, let's erase some of this. We're going to have the limit as b approaches infinity of this plugged in negative 1 over x with b to 1 as our bounds. And then from here, let's just plug in what we have. We have limit as b approaches infinity of negative 1 over b minus 1 over 1, so plus 1 over 1, which is just going to be the limit as b approaches infinity of negative 1 over b plus 1. Now, what are we going to have from here, right? We had something somewhat interesting. So if we remember our graph, it looked like if this was the y-axis, it would look like that and then that. But we're starting at 1 and then we're going to infinity. Since we're starting at 1, we're already relatively short, and when we continue doing that, we will get a finite value if we're doing a limit. Obviously, if we weren't doing a limit and you had just an infinite amount of space underneath there, regardless of how small it'll get, so at a certain point, like once you have, say, 1 over 2 trillion, I don't know how many zeros 2 trillion is, but 1 over some enormous number, it's obviously going to be a very small value, but it still is a value, and it will continue to increase the area under the curve, but we're doing a limit, it's not the actual. So as limit as infinity, okay, I can speak English, as the limit of negative 1 over b plus 1 is where b approaches infinity, we'll have negative 1 over infinity plus 1 if we were to, plug in infinity for b, but that's not going to work. When we try to think of negative 1 over b, we're going to have a very, very large number under 1. So 1 divided by some very, very large value is a very, very small value. So we're going to have 0 plus 1 is what this is going to be equal to. So 0 plus 1 is 1. And yeah, we did talk about why the limit as 1 over n or 1 over x as n approaches infinity or x approaches infinity, or in this case b approaches infinity, this limit's going to be 0. And as b approaches infinity, 1 does not change. So we're going to be left with simply 1. So yeah, it's not easy. I mean, it's definitely not as complex as it might seem. It's relatively normal in terms of what we're doing, because we're just combining what we know about limits and what we know about integrals. We have done infinite limits. We did infinite limits a long, long time ago in school. Not me and you doing it, but we did infinite limits a while ago in terms of n behavior. But now we're just redoing infinite limits, but we're applying them to definite integrals. But yeah, so let's do another one. Okay, what's another normal looking one? Yeah, okay. Let's do the integral from 1 to 0, from 0 to 1 of 1 over square root of x dx. 0 to 1 of dx over root x. Now, 1 over root x is not going to be a super nice looking function. If we were to actually draw this function out, we would have some kind of a... It's hard to fully actually show, but it's gonna be like that. This is x, and this is like y. It's gonna be like automatically extremely large y values, or well, not extremely large y values. It'll be extremely large x values for rather small y values. Like let's say we have 1 over 100 in that x value. 1, I'm not gonna write it next to that, but we do 1 over root x, and if x is equal to 100, we have 1 over root 100, and we're only at 1 over 10. Like, yeah, it's actually a lot closer to like a negative exponential function. So if we have this is equal to 1, we'll be very close to 0. So it'll be like 1 over square root of something very small, and then it'll just kind of plateau, and it won't increase. I don't know why it's looking like that, but it'll just decrease rather slowly. Like, I wish I was better at drawing. But like, say this is 144, we'll only be at 1 over 12. So yeah, it'll decrease, but at a much calmer pace. And we're only going from 0 to 1. So we should have a relatively large value. But let's actually do this integral out. Since we're doing... This is going to be that A to C notation where we're doing a somewhat crazy looking limit as C approaches B or A. This one's going to be... I think this one's actually going to be B. Yep, because B is what we... Wait. What? No. It's going to be A, I think. Yeah, it's going to be A. So we're going to have A plus, because again, if this never... You can't have 1 over root negative... Not 1 over negative x. 1 over square root of x. This will never have a negative x value, because when it does, you won't be able to have a real root. You'll have imaginary roots at that point. So it'll never actually go past the y-axis in the x direction. So this will be approaching 0 from the right, which is c approaching a plus, of this integral from c to b, because again, we're just going to be plugging a for c, because usually we would have that integral from a to b, but right now we can only approach a, we can't actually get to a, so we're going to plug in c instead, and then we're going to have the integral of f of x dx. So let's do that same thing. We have the limit as a approaches 0 from the right of a to 1 f of x dx. And then, well, we didn't actually define f of x dx. This is just going to be dx over root x. So this is going to be x to the negative 1/2. A to 1, x to the negative 1/2. And so let's do our n plus 1. 1 over negative 1/2 plus 1 times x to the negative 1/2 plus 1. So we're just going to be left with 1 over negative 1/2 plus 1, which is 1 over 1/2, which is going to be 2, times x to the negative 1/2 plus 1, which is going to be 1/2, or 2 root x. And so let's plug these values back in. Yeah, let's rewrite what we have. We have the limit as a approaches 0 from the right of this integral from a to 1, or, well, we actually already got this integral from a to 1, so we're just going to plug this into 2 root x from a to 1, so we're just going to be left with the limit as a approaches 0 from the right of 2 minus 2 root a when we just plug in what we had originally. So yeah, plug in 1 for there, a for there. And then from here, we are doing the limit as a approaches 0. So we will just directly substitute 0 for a, and we're just going to be left with 2. So when we plug in a equals 0, we'll get 2. And again, it will look like an infinite area under the curve, right? If we remember our graph, it can never intersect with the y-axis, so it'll just continue going upwards. If this is 1, this will just continue to go upwards, and it will obviously just be an infinite area under the curve. But we're doing the limit, right? This is an infinite limit. And if you thought of this as maybe this was the y-axis and then this was the x-axis, it might be easier to see that this is actually an asymptote, where as y increases further and further, the actual value will be much, much smaller. The x value will be like 0.00000001, and at that point the area under the curve will be negligible, and we will have a general area being close to 2. So yeah, that's an improper integral. We'll do some more, and we'll also do some multiple integrals. Alright, so let's do some, well, not multiple, let's do some improper integrals for practice. Let's search something up real quick. Alright, so we have, this one's going to be fun because it's going to combine two of the things that we were talking about so far today, and that's improper integrals and integration by parts. So let's do it. We have the integral from 0 to infinity of e to the negative x times 1 plus 2x dx. Now this is going to be one of the more common types of improper integrals where we have an infinite limit. So let's set t is equal to infinity, or, well, t isn't equal to infinity. T is just like a value that we're going to substitute for infinity. So we have the limit as t approaches infinity of this integral from 0 to t of all of this. Now, when you have something more simple than, say, root x squared, or like, not root x squared, 1 over root x, or 1 over x squared, something like that, it's a lot simpler to just ignore the bounds really quick and just solve what would happen if we were just to integrate this. Because again, definite integral is just going to be a regular integral, but we have to plug in our bounds. So let's just assume that we were actually doing an indefinite integral of this, like that. We have two functions, so this is product rule that we're going to need to undo. So let's say u equals something, dv equals something, v equals something, and then, well, messing up how we wrote that, du equals something, and then and then regular v equals something. So which of these is going to be easier to integrate? I think probably this one. Well, this is, again, a matter of debate. You could say that this one's easy to integrate, and I mean, it's not too bad to integrate, but it's a lot simpler to integrate this when you are only differentiating this. As we said, derivative of x is just going to be 1, derivative of a constant is going to be 0, so we have 2 times 1 for du. So if we let this be 1 plus 2x, we're only going to be left with 2dx. That was quite possibly one of the weirdest x's I've ever written. 2dx. And this is going to be a lot easier to do that v du, or the second part of our integration by parts formula with. So now that only leaves us with dv is equal to e to the negative x dx. So let's let e to the u equals negative x, u prime is equal to negative 1. So if we want to undo this u prime times e to the u, so 1 over u prime, even though that's not a rule for this one, it's going to work. I think it'll, just as a general rule, if you have a linear exponent, then you can do this 1 over u prime times e to the u with. And then you just get -1 times e to the u, which is negative x. So we're going to have negative e to the negative x, which, again, you could maybe be able to use 1 plus 2x as v, but I think for our purposes it's going to be a lot easier if we let e to the negative x dx be our v. Now from here, let's do uv. So we're going to have uv is going to be negative e to the negative x times 1 plus 2x minus v du. So we're going to have minus minus, so I'm going to put plus e to the negative x du, or 2. So I'm actually even going to bring that 2 out front too. So we're going to have dx, and then 2 is going to be our constant. And then from here, this one is, again, a rather easy integral to calculate, but we already did that, so I don't think it's necessary to redo it. We're going to have negative e to the negative x, 1 plus 2x, e to the negative x plus c. Whoops. It's going to be minus 2 times e to the negative x plus c. And then from here, let's think what we're going to do. Well, we can actually simplify this a little bit. So we have negative e to the negative x times 1, so negative e to the negative x, minus 2 times e to the negative x, so we're just going to be left with 3, or negative 3 e to the negative x. So when we pulled out that negative e to the negative x, we're just going to be left with 3 plus 2x. And then this is, again, going to be plus c. Now, let's actually plug in our definite integral. So let's rewrite this. So yeah, let's plug in our bounds. If this negative e to the negative x times 3 plus 2x plus c is the antiderivative, then we're just going to have to rewrite this as our original function. We have the limit as t approaches infinity of the antiderivative of this, where you plug in t for infinity and 0 for 0. So we're going to have negative e to the negative x times 3 plus 2x with the bounds of t and 0. Alright, and so let's plug these in. We're going to have negative e to the negative t times 3 plus 2t, and then we're going to have negative e to the 0, so negative 1, and then this is going to be 3 plus 2 times 0, which is 3, so we're going to have negative 1 times 3, so positive 3, which we might, actually I don't think we need to do anything to like make that simpler. From here we simply do the limit as t approaches infinity of this. Now, this one's an odd one, right? We're going to have some interesting stuff to do. We have negative e to the negative t. So we can write that as negative 1 over e to the t. And then this is going to be multiplied by 3 plus 2t. Now, if we did t approaching infinity, t approaching infinity of this, well, we would get infinity, right? If you do e to the power of a very large number, and then you do 3 plus 2 to a very large number, well, this is going to be infinity, and this is also going to be infinity. But it doesn't quite work in, well, I don't want to get too technical, but you can't cancel out these infinities. I think I might have talked about it in my limits videos, but infinity, well, 1 over infinity times infinity, or infinity divided by infinity, isn't going to be cutting it. we're going to have to do L'Hopital's rule to actually get this. So let's ignore this 3 for a second. Well, we don't have to ignore it, but if t approaches infinity, 3, just plain 3, does not take t as input, so regardless of what value t is, the limit as t approaches infinity of 3 is going to be 3. So we have 3 plus 2t, well, negative, all over e to the t. Again, e to the negative t is 1 over e to the power of t, and if this approaches infinity and this approaches infinity, and we are doing a limit as t approaches infinity, we can do L'Hopital's rule. And from here we have to do the derivative of the numerator and the derivative of the denominator, so derivative of a constant 0, derivative of x or t or any single variable is going to be 1 times 2, it's just going to be 2. And then the derivative of e to the power of t is going to be e to the power of t, negative. And then again, e to the power of t approaches infinity, but 2 approaches 2. So 2 over a very, very large number, it could be, it doesn't even need to be 2. It could be like 1 trillion over a number larger than 1 trillion is eventually going to be approaching 0. If you have a normal value over a very, very large value, you are going to get a very, very small value. And so we call that 0. Oops. We have 0, and that's the limit of this. And then we said the limit of 3 as t approaches infinity is going to be 3, because 3 does not take t as input, so it won't be affected. So we're just going to have 3. Yeah, I honestly don't think improper integrals are too difficult to understand. It's just, if you ever have a limit that does not have possible bounds, like if you are working with bounds that aren't like workable, infinity, or if you have like a bound that is changing, or anything that has an asymptote, anything that's not technically possible, if you can't do something that's possible, you can do something that's kind of possible, which is what we did with L'Hopital's rule, which is what we've been doing with limits and how they affect derivatives. But limits are going to be your best friend when you have something that seems impossible, but you need to make it less impossible. Because limits don't really evaluate anything. Sure, you can plug in limits, and that's direct substitution. It does work like that. But limits, especially infinite limits, give approximations, which is a lot more important in the grand scheme of things for these kinds of improper integrals. Because again, if you were to treat them like proper integrals, you wouldn't be able to solve them. You would just get either infinity or some type of error. But yeah, that's an improper integral. And then very, very briefly, we're going to talk about some multiple integrals. I'm not actually going to go into too much depth in this because we've been keeping it relatively univariate for most of my videos, and if I just spill off into multivariate, we're not going to have a fun time. But we are going to do a little bit of multivariate. So we have f of x, right? We know that if y equals f of x, then y is a function of x, which means that it only has a singular input. But if we have f of x comma y, that means that we have two separate inputs that both affect the actual function's output, which gives it another dimension. That's why you might see things like the xyz axis, or there are also 4D like quaternion like axes, but that's not what we need to do right now. So we have, say, if this is y and this is x, then there's also a z. If this is x, y, z, z is depth, y will be vertical distance, x will be horizontal distance. But when you have multiple inputs, your output will be a increased dimension. If f of x is just going to be on this curve, then f of xy might be a three-dimensional solid. So if we were to do definite integrals in a three-dimensional solid, let's think about what our definite integral with a two-dimensional solid is. We have area under the curve, right? So if we add another dimension to area, if we add depth to area, let's even draw this out real quick. If you have the area of the base of a square, right? X and x, so x squared, and then you add another dimension, you add this depth of x. For example, you are going to get x times x, not x squared times 3. It's going to be x squared times x, which is x cubed, or a cube, right? And if you could solve for area of the base and then you added another dimension, you're going to be solving for volume. That's what we're doing when we do multiple integrals. Just to very briefly show you what they might look like, even though we're not going to actually do anything just yet. Let's say we have, I don't know, let's say we have this, and then like f of xy of some type of dx, dy. This is going to be area. I mean, this is area, but this is going to be volume. You're adding another dimension to your integral. So instead of just calculating area, you're calculating volume. And that makes sense. If you just look back at geometry, if you calculate the area of the base of some type of triangle, rectangle, anything, and then you give it depth, you give it another dimension, you're going to be solving for volume. And that's just food for thought. I don't really want to get too into double integrals or, even triple integrals. I don't think that's strictly necessary. But we can do some relatively normal looking ones. Let's have the integral of, let me just search up some examples real quick. Alright, so the first example that I see, it's relatively normal. We're going to have, I'm only going to do like one or two of these examples. I don't want to get too into the nitty gritty, even though I might do some multivariable calculus in the future. I just, as of right now, want to keep it relatively within our scope of understanding. So the integral of 1 to 3 of the integral of 2 to 4 of 9x cubed y squared dy dx. Now, I wish I could illustrate what this might look like. I might find some type of a calculator and then plug this function in to show you what the actual image of the thing might look like. I'll probably do something like that in the description, but let's just show you how you might solve these integrals. And the solving, at least of these more normal multiple integrals, is going to be relatively similar to what we've been doing. We're differentiating with respect to y first, because this integral from 1 to 3 will be not differentiating, we're integrating with respect to y first, because this integral from 1 to 3 will be integrated with respect to x. And if these were switched, then you would have to integrate with respect to x and then integrate with respect to y for that integral from 1 to 3. So I know I'm kind of, not explaining what's happening too well, but we're just doing the definite integral of another definite integral, at least for now. So we're integrating with respect to y, which means that x is going to be treated as a constant for right now. We're going to have y squared, so 1 over 2 plus 1 times y to the 2 plus 1, so 1 over 3 times y cubed, and then 9 over 3 is going to be 3, so we're going to have the integral from 1 to 3 of this value 3x cubed times y squared, not y squared, y cubed. And then with the values y equals 4 and y equals 2. So from here, let's just plug in what we have. 4 cubed, let's see, 64. Yeah, that sounds right. 64x cubed minus 24. So 2 cubed is 8 times 3 is 24. So, times 3. So, what's that going to be? 64 times 3 is, should know this, just off the top of my head. 192? Yeah, 192. So we have 192. I'll do the integral from 3 to 1 Oh, and this is going to be, again, with dx at the very end. Because all of this operation, like this integral from 2 to 4 of 9x cubed y squared, is going to be done within this larger integral from 1 to 3 with respect to x. So that dx is going to be at the end as well. And then we have 192x cubed minus 24x cubed, which is going to be just 1 with dx at the end, 168x cubed. Okay, and then from here, this is going to be another relatively normal one. We're going to have 1 over 3 plus 1 times x to the 3 plus 1. So 1 over 4, 168 divided by 4 is going to be 25 plus 17, 42. Yep, 42. And then we have 42 times x to the power of 4. And you have 3 and 1. We're just, I mean, like, I'm not really showing you how this is working too well, but you're gonna integrate with respect to your first, like, dx or dy or dz. You have to integrate with respect to your first one first, and then once you finish evaluating that first integral, you have to do it within the other integral. You can kind of think of it as you have your input with respect to one variable, and then you have to do the outer integral with respect to another variable. And then this is going to be from 3 to 1. I don't know why I put a 1 there. All right, from 1 to 3. And 3 cubed is 81 times 42. That might be a little bit ambitious to try and do my head. 81 times 42. So 3,200 plus... No, I have to do this out. I'm sorry, I'm not a robot. 81 times 42. 2, 16, 84. Wait, what? Yeah, 80. No. Okay. 432, so 324. I don't want to erase any more important work. I might do this up here. So we have 81, 42, 82, 324. So 2, 2, 3, 3, right? 32. No. Wait, what? Man, now I have to actually do stuff. Oh, 81 times 2 is 162. That's where I'm wrong. Let's write this again. 162, and then 324. So we're going to be left with 2, 0, 4, 3. Okay, 3402 minus, what's that going to be? We plug in 1. Oh, that's just 42, so minus 42. And that's just going to be 3360. So we're going to be left with 3,360. And this is, you can kind of think of this, we'll put U for units cubed. This is going to be the volume under this, like, it's not really a curve, it's more like a shape. The volume under this, like, shape is going to be this, within these bounds. A 4 to 2 on the y, and then from 2 to 4 on the y axis, and then 1 to 3 on the x axis. So yeah, I mean, again, that wasn't a perfect, like, explanation of what's going on. It's just a way to, I'm just showing you how you would evaluate some of the more simple multiple integrals out there, and kind of like an introduction to the idea that if you add another dimension to definite integration, you are going to have, instead of area under the curve, you're going to have volume. And then let's do another one. Let's do just something relatively simple. I don't want to get too into the weeds. Okay, and I think I'm actually just going to do a relatively simple one, just to really emphasize why this is considered volume. Let's do constant function. Let's say that f of xy, regardless of whatever inputs x and y are, will be 2. So let's draw out this. Oh. So I'm actually going to make an executive decision to say that z is equal to fxy. Xy can be anything, and it could even probably be on the xy plane, but there's a lot of weird stuff with these kinds of things, and it'll make it more difficult to graph. I only want to say that if this is xy and z is considered depth, then z is equal to xy. And so if this is xy and that's 2, then our graph is just going to be f of xy is equal to 2. That's not the greatest. Yeah, it's not starting at the xy axis. It'll go past, it'll go outwards, but yeah, I might even draw some arrows to really show what's happening. If we look at that, this is going to be z equals f of xy, where that not little, it's going to be large, square smack dab in the middle of the z-axis is going to be equal to 2. And from here, I might even try and rotate my drawing, not like actually, but if we say that this is the xy, and then this is the z, and we have this square, because again, this is going to be a square. I'm not great at drawing 3D things. It's more like just saying them. But yeah, this is going to be what the graph z equals f of xy is going to look like, right? And from here, if we were to make our bounds, say, what was the original problem that I was supposed to do? We are supposed to do the integral from 3 to 6 of the integral from 2 to 4 of f of xy dx dy. So if we were to, look at 2 to 4 first, let's draw 2 and 4. That will be some, we can even draw some lines there. That will be that area. And then y is equal to 4, and it's going from 3 to 6. It's getting a little bit cluttered, but it's just going to be that rectangular prism. So when you have this double that was, looking at it now, I thought it was okay, but just blinking and then taking another look at this does not make any sense. Maybe I'll do what they do in engineering. I'll do a side and top view. So we have x and y, right? We have from 2 to 4 on the x-axis, and then from 3 to 6 here. And we have this being our front. If you were to look at the xy axis head on, you will get this rectangle, right? And this is going to be 2, if you looked at the area of this base, it's going to be 2 times 3. So we're going to have 6 out here. And then on the z-axis, let's try and draw that. It'll be let's do a top view. If this is the z-axis and say this is the x-axis, you are looking directly. If the y-axis could be, it'll be like that. But since we're looking directly face into the xy axis, it'll be into the xz axis. It'll be somewhat like this looking, And so if that equals 2, then yeah, we're kind of done. Well, this is going to be equal to 2 because z is equal to f of xy, and we said that f of xy is equal to 2. So if z on this axis is equal to 2, let's kind of draw without any axes, just like draw what's happening a little bit, we have this kind of, even without the axes, I don't know how to draw. So we have this nice looking rectangular prism, right? We have the integral from 3 to 6, and then the integral from 2 to 4, and then z, or f of xy, is equal to 2. And so this is just going to be the area of the base. So 3 times 2 times 2, so z. So just to generalize what we've been doing, let's write down our original problem, the integral from 3 to 6 of the integral from 2 to 4 of f of xy dx dy. Now, if this is equal to 2 dx dy, we're simply just going to take out that 2. Multiple integrals follow the same integral rules as normal integrals. So when we take out that 2, we're just going to be left with 1 here and 2 here. So if we are integrating with respect to x, wait, what did I do? Oh, yeah, no, this isn't right. It's going to be, if this is the xy axis, like if this is y and this is x, we're going to go from 2 to 4, and then from 3 to 6. So I'm not sure if I did that wrong also in the actual thing, but since we're doing dx first, and our bounds are from 2 to 4, this is going to be 2, and this is going to be 3. I don't know why I drew correctly if I was going to actually write the bounds incorrectly, but you know, it's whatever. Yeah, 2 to 4 is going to be our like base length, or x, and then this is going to be our base height, so y. And then z is equal to 1, but we brought that 2 out, so it's going to be just x, y, z. And so this integral, 4 minus 2 is 2, 6 minus 3 is 3, so 2 times 3 times 2, and that's just going to be 12. So, yeah, another way to write this is just going to be area. Area of base times z, or f of xy. And that's how you would solve multiple integrals of constant functions. But you're most likely not going to get those relatively simple ones. I was just trying to illustrate why volume is the integral of an integral, right? You're just having area under the curve, but you just give it another dimension, so it's going to be volume. And yeah, I mean, that was by no means a good explanation of how multiple integrals work, but I hope you kind of, sort of, maybe get it, and at the very least, you know how to do 2 multiple integrals, and yeah, I mean 2 types of multiple integrals, which is more than enough for now. And yeah, if you enjoyed this video, please comment down below. This one was relatively short, so I think I'll still give an album. Let's see what I've been listening to. I have been listening to I don't know. Been listening to pretty much the same stuff now. I guess I've been listening to Planet Her by Doja Cat, but who hasn't? Let's see. I have been listening to well, yeah, I mean, it's, yeah, sure. I've been listening to the Vince Staples self-titled EP a little bit, and I was hesitating about suggesting this one because this is, I mean, it's definitely a fantastic body of work, but to call it an album is pushing the definition of album. This thing's like 20 minutes. But it's obviously very good. Vince definitely has this like world-weary kind of melancholy worldview, and I mean, it's not happy music, or It's not particularly inspiring or anything, but it's definitely interesting, and that's more than enough. And so yeah, instrumentation's obviously very good. Kenny Beats does come on here quite a bit, I think. I think he actually produced the entire thing. I'm not sure, but yeah, the production's always on point because it's Kenny Beats. Rapping's on point because it's Vince Staples, and it's 20 minutes long. If you have a good little bit of time to kind of knock out, I think this is a perfectly fine way to do so. It's not like the greatest thing I've ever heard. It's not. It's definitely not bad by any means. It's definitely good, but it's not meant to be anything more than what it is. And I think it's also reflected in how short it is. But the ideas on here have been things that he's talked about before, things that I want him to expand upon further, and things that are definitely enjoyable. So, yeah, Vince Staples by Vince Staples. Listen to it if you like. And if you like this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then, well, man, it's been a while since I've exercised. Do some high knees. Yeah, do some high knees. All right. Bye.